recording. And today I will, as for some of the challenges, I will give like the almost around the right at the end the solution kind of thing. But for some other challenges, I will give you a brief hint about like how you can approach the challenge. Yeah. And let me share my screen. Then in week 7, we have several challenges, and then these challenges are different with the what others we have solved. We have been solving in the other weeks, because in that week, in each week, we have some of the themes about about the challenges. For example, week 2 was buffer overflow. Week 4 was avoiding differences. Week 5 is ROP. Week 6 is arbitrary read and write and format string. Then week 7 is more like the mixture of like system knowledge and also for the attack knowledge kind of thing. So these challenges are more realistic in some sense, and then like you can have another surprising factor that like the machine works weirdly, and then how we can control that. And let's start with the first challenge, the 0 run command. And always don't forget to read about like the some of the readme in there. And then like the program is about, yeah, so these readme links you can reach to there, and then try to learn about like how you can use the shell commands. So in shell, there are some of the special meanings of some like this kind of the characters. For example, ECHO is something like printing some of the argument that I supplied. And then if you do echo ID, then it will print ID. But if you do backtick, the like round up the backtick with the ID with the backticks, then like it will actually run the command ID and then put the output of the command as the argument of this one. So for example, to search about like where the ls is, so we can do which ls, and if we do echo which ls, then it will just print out that use this as an argument. So it's something like the result of execution result of this command will be the replacing this argument. Yeah, it's something like that. So there are some of the special commands, and also like if we do ls this kind of the right arrow and then a.txt, and it will output the send out data to the file. So we can redirect the file, and also we can read the file, for example, in the different directions. So if we do this, then it will put the a.txt to the shell this program. Yeah, and also we can deliver the output to the other program like this. So for example, if we do this, then the output of the ls will be supplied as a standard input to the cat. So that's the pipe. So we can also do something like this to maybe see the result page by page. So we can use a less, more, or this kind of a command. That's how shell works. So after you learn about that, and let's check about the code. And in the code, what it does is it will set the path environment variable to /bin, so you cannot play the trick with the path environment variable at all. And what it says is this is a secure ls machine, and it says like which directory do you want to take a look at, and you can supply your input to user arguments, and it will go over the checking, and then user arguments, it gets the input with the %50s, so the maximum 50 characters, and user arguments are size 64, so there's no buffer overflow vulnerability. And the check input, it checks each character if it has some of the bad characters. So bad characters are dot, slash, semicolon, and pipe, and backtick, and quote. So that we cannot the backtick, yeah, we cannot use like these kind of the commands. So we cannot do something like this, yeah, because this backtick character is prohibited here. And then after, if it detects a bad character, it will do exit -1, so we cannot supply any kind of the bad characters. And then after passing this check, it will run ls-l and then our arguments. So this is why it says about like the directory. So if we supply some of the directory name, then it will do ls-l. Yeah. Then it will run that as a command at the system. So that's the basic structure of the challenge. And then the challenge might be like how can you run the arbitrary command here by bypassing this kind of check. Yeah. So if we run the command, if we just type a flag, then it will just run ls-l flag. Yeah. But if we do something like, and right now it says like the flag permission denied, but suppose we create some of the fake flag. Make it something like this, and then we can inject some of the data here. And suppose we inject cat fake flag, then it shows the contents of the fake flag is here, something like this, yeah, as an error message. So if we can run this command like this, then we can get the content of the flag. But the problem is that even if we try this, then it says like we have a bad character, the backtick. Yeah, so that we cannot use backtick. But if you study a little bit about like some of the commands in here, then you will realize that this dollar parenthesis ID and parenthesis, this may serve as a what is that? Similar to the backtick. So you can actually do this, this, and then this dollar parenthesis. Yeah, these characters are serves as a backtick. Yeah. So what you can do is, so for example, so if we do something like this, then it says like it had no such file or directory or something like this. And let's try with the run command. Yeah, then it says ID not found because ID is a user bin ID. Yeah, so we know that it changes the path to the bin, but we cannot specify any kind of the directory thing. So what we can run is just a command in the /bin, because for the otherwise, if we want to run like a user bin ID, then we need to run user bin ID. Then this character is slash is even slash is prohibited, so we cannot use that. Yeah. So what we can do is maybe not ID, then what's in /bin? Maybe we can run ts. Yeah. So if we run ps, something like this, it's something like this. Then if we do echo ps, then it will show something like this. And let's try let's try ls-l ps. Then it shows each entry like this, but at least we can read that. And we will try run command ps. Then it actually runs a ps inside there. So at least we know that how to run the command using dollar parenthesis. But what you want to do is maybe catflag. Yeah. But it does not work because in some of the syntax it does not allow like having the white space here. Yeah. So right now you can run the arbitrary command by having the dollar parenthesis and then typing command and then closing the parenthesis. But please think about like how you can bypass this kind of the syntax error and successfully inject the command the catflag and get the results something like no, fake flag. Get the results something like this. So you can, if you can run the command, then you can get the flag in the error message. So any question to this challenge? All right, so this one is not the difficult one. After you realize that the dollar parenthesis, this works like a backtick, and you could you're a little bit away from the getting the flag because the cat space flag that does not work in the program. But if you can remove all the white space, yeah, then you can run your command and then get the flag. Yeah, that's the important thing. And then let's move on to the next one. So next one is the guess my random, and then let's take a look at this readme first. So it says, don't ever guess the random, exploit the vulnerability. And then let's check the source code. So the main function calls the read random. Then this read random function, there's like the open dev view random, and then read 4-byte size of the 32-bit integer, and then close the random. And now we have the random integer. Then that should be not 0. And then it will do as printf random string. Yeah. So random string will be printed out as a randval equal, yeah, and then %p means like it will print out 0x and the hexadecimal number of the random int. And then it says a printf %f as a random string, but in the program it does not have that string. That's for test, and then this line is not in there, so please ignore this line. So what it does is like it will create a random string like this and then store in somewhere in the global buffer area. And then it will run target. And in the target function, it has a maximum buffer size, and then both buffer sizes are 64. And then it runs app-gets, so to receive the data into the buffer, but with the maximum buffer size, so there will be no buffer overflow vulnerability at all. And then it will run the sprintf for like the print out the string randval %s buffer. So the generate the similar string with this kind of thing. Yeah, and then based on your input. And then if that construct string is the same with the random value string, then it will pass. Yeah. So that's the structure of the program. And then like you might see then like there's a no buffer overflow vulnerability at all. And because this random string is generated by dev urandom, and it seems like you need to purely guess this random value, but that's not the challenge. There is the point that you can launch the buffer overflow attack, and that is, so think about what is the maximum size, available size of the buffer, and you can type up to max buffer size, which is 64-byte. So you can fill up to entire 64-byte of the buffer, and then it will run sprintf. And then think about what is the maximum size of the string. So this string is defined to have like a maximum 64 bytes, but the thing is, so it will print out 1, 2, 3, 4, 5, 6, 7, 8, 9 bytes, and then %s buffer. And what is the maximum size of the buffer? It's a 64. So there are 64 bytes, and then we can overwrite 9 more bytes. 9 bytes and then 64 bytes. So we can write 73 bytes to the string. So this is where the buffer overflow vulnerability could happen. So the challenge is that is for asking that you can identify this as a buffer overflow vulnerability, and also exploiting this vulnerability to defeat this and execute this function. Please run this, then you can get the shell. So again, so this challenge is about like exploiting the buffer overflow vulnerability at the string buffer, and you can tweak this sprintf by sending your input, malicious input to the buffer. And if you can overwrite the return address or some other control data, then you can successfully run the different function. So that's the challenge. Any question to this challenge? So the important thing is like don't ever try to guess the random number. So it's quite a secure random. So yeah. And then next move on to the next one. Yeah. Then let's read readme first. And it says please create a buffer overflow vulnerability by exploiting a format string vulnerability in the program. So it says we need to create a buffer overflow vulnerability by exploiting the format string vulnerability. And then in doing that, we need to bypass the stack canary too. That means on check success, like this program was with the stack canary. So it seems like it has a buffer overflow vulnerability. It says like a title says one format string, the format string vulnerability, and then like it says like we need to create a buffer overflow vulnerability. And then let's check the source code. So the program is very simple. Main function runs target, and this target function has a buffer, and its maximum size is 64. And the integer pointer size points to the global variable max read size 63. Yeah, and then it says please type your name. Then it will read up to the size of the maximum read size. So it seems that it reads up to 63 bytes. Yeah. And then after reading the 63 bytes, it marked the 63rd character. So the last character is a null to mark the entire string length as within the 64 byte. And then run printf. So this is definitely insecure because the format string is a controllable value. And then you can launch some attack to do something. Yeah. And then it will do the get your input again and then run a secure version of the format string. So this is not the format string vulnerability at all, but think about this one. So this also read to the buffer with the size value, but you can think it as like the size value is set as like the address of this one. And then if we dereference that, then it will return 63. But if you can use this format string vulnerability, as the changing the value of this one from 63 to some value larger, 100 or something, then you can trigger the buffer overflow vulnerability here. So one of the things is like to exploit this format string vulnerability to change the value of this one. Yeah. So you can apply the arbitrary write. So so the binary is a non-PIE. So you can launch the arbitrary write to change the value of the maximum read size. Yeah. And then if you can change that, you can trigger the buffer overflow vulnerability here. But at the same time of the changing the this value, because this program was with the stack canary, so you need to leak the stack canary here and use that value to when you launch the buffer overflow attack. So this is an example that like this code is all secure if you do not have this format string vulnerability. But by having a one format string vulnerability, you can make the entire program insecure and allowing attacker to achieve arbitrary code execution. So I included this challenge to guide you guys to learn about like having the one insecure code, one line of the insecure code can detonate like an entire security of the program. Any question to this challenge? So this might be easy after you figure out like how you can change the value of this one. So just apply arbitrary write, and at the same time, you need to do arbitrary sequential leak to leak the stack cookie value. Then let's move on to next. So next is 2048 challenge. Then readme says like it says, are you good at like the 2048? And then can you score more than 4 million? And then some link, and then in some link it says like what will be the maximum possible score in 2048. And then if you run it, you can actually play the 2048 game. Then maybe some of you are very good at like playing this one. Yeah, I'm not that good. Yeah. And the interesting thing is that if you examine the code, so definitely there's a code for reading the flag. So if your score goes more than like this number, about like 3.9 million, yeah, Then it will read the flag and then print out the flag. Yeah, that's it. So it says like you need to get the score more than this one. Yeah. But it's very difficult to play this game hard and then get this score. But the actual challenge is about like you need to hack this program and then make the score bigger than this one. And to do that, let's examine what is the type of the score. So the type of the score is short. Short means 2-byte integer, and then short means a signed one. So we can specify integer types, something like there's a byte, actually character. So this is a signed 1-byte data type. And short is signed 2-byte data type. And then unsigned 1-byte is an unsigned character. This is an unsigned 1-byte. Yeah, something like that. And then unsigned short is an unsigned 2-byte. Yeah. And then there is an int and unsigned integer. And then these are 32-bit. And then it will be corresponding to, for example, the short and short is like it's equivalent to int 16t because it's a 16-bit, and then unsigned short is equivalent to uint 16t. So nowadays developers are using like this kind of the data type because that depending on which machine you are. So for example, long is a 32-bit in Linux machine. So no matter in 64-bit machine or 32-bit machine, long is 32-bit in Linux machine. But in Windows machine, long is 64-bit. Yeah. And then in Linux, in Windows, and then in Linux, 64-bit integer is a long. Yeah. 64-bit integer in Linux. And then long is also a 64-bit integer in Windows. So there are a little bit of confusion. So if we just specify the data type as a long, then it could be 32-bit in Linux and then 64-bit in Windows. So to avoid such a problem, nowadays the developer uses int 64t, then uint 64t, yeah, something like that. And the important thing is that our score is defined short. That's int 16t, which is a 16-bit integer signed. And then what is the representable value range of this one? So for 16-bit data, we could represent up to 2 to the 16, which is a 65536. And then if it is a uint 16t, then we can represent from 0 to 65535. So entirely 65536 numbers. And then if it is int 16t, then we can represent it from the minus 32768 and then to 32767. Yeah. So entire 64536 numbers. Yes. Then the reason why I represent the numbers like this is that like this kind of the values may overflow. That means like suppose we have an int 16t a and the its value as the maximum value of the int 16t. Then what will be the value if we do something like this? The +1 over the value. Then a must be the 32678. And that will be, so if we represent this as like the, what is that, the hexadecimal numbers, then 10000 is 65536, and then half of this is like the 8000 is like the 32768. Yeah. And then like so the 0x7FFF will be the maximum value of this one. And then if we do +1, then this will be 0x8000, then which is 32768. But the problem is that this is actually the value of the 1000000000000000 in 16-bit representation. And then if we represent this as a signed 16-bit, then we will use the top bits as a signed one, and then rest of the thing as the normal bit representing the the number. So what we will have is, so if we add 1 over like the 32767, then what we will get the minus 32768. So we will try that. So what we know is that the score is a short. Then let's write a program, theta-c. Then what we will do, write a main function. Then short score is 32767. Then it's an unsigned integer. So print it as a score, short integer. Then we will print score is a score plus 1. And then printf %u score. Yeah. And also we will do %d. So we will see that what is the value of the unsigned value and then signed value. Yeah. And make t and then run it. So what we are seeing is like a completely different value, and I believe if we, I'm not sure if this is a correct syntax or not. Yeah, right. So if we restrict all the values as a 16-bit, then that's h and h, u, and hd. So which is a 16-bit unsigned integer and 16-bit decimal integer. So at the start, the value was 32767. So that's all okay. And if we add 1 for the signed, the unsigned value, so the value is 32768. But for the, if we represent that as a signed value, then that will be minus 36768. Yeah. So there's a signed value, unsigned value mismatching. And then suppose our score is 0. And then what if we deduct value 1 from the score? Yeah. So suppose our score was 0. And then if we deduct the score by -1, yeah, then what will happen? Then, so the value itself was 0, and then after deducting 1, so if we represent that as a, interpret that as a signed integer, then that will be -1. But if we interpret that as an unsigned integer, then that will be this kind of the large value. Yeah. So that's the main idea. So it's something like if we make the value as a -1, then we can hit some of the big value like that. But the interesting thing is that, interesting thing is that although the score is defined as a 2-byte integer, yeah. So in the data type, like it will use like a 32-bit data for comparison. For example, so in this comparison, this value is 32-bit data. So if you have a negative value in the score, then it will be extended as the 4-byte value and then be compared with that. And if you actually make your score as a -1, then you will get the value as around 4 billion, because the comparison will interpret the entire value as a 32-bit, because the comparison target is a 32-bit value. So this is definitely bigger than the 65,000 or something. So not represented by the short integer. So that's why it is coursed by the C language to 32-bit integer. So our objective is like to make the score as a negative value, then it will trigger the variability. So for example, interesting thing is like if you make a wrong move, then it will decrement the points. So you can keep decrement the points towards like 0.0, and then due to the signed unsigned mismatch, the score need to be -1, but it will be interpreted as a unsigned integer value, and finally you can get like this kind of the big number. So this kind of the integer overflow variability underflow, this is actually integer underflow, because we subtract 1 from 0, and then that's why like we could have like this kind of a weird value. And then this is this is a quite frequently happening vulnerability. So one of the interesting thing was like in the Ethereum blockchain, it uses a 256-bit integer as a main data type. And then there was an integer underflow vulnerability, so demonstrating that like how many tokens you have or something like that kind of variable. And then you can give out some of the tokens to the others if you have enough token. And then hackers somehow managed to like deduct more tokens than that they have. Then they would get their variable as negative values like this. But the interesting thing was like that's a uint 256t. So if hackers can set their token value as a -1, then what they can have is like actually 2 to the 256 number of the tokens, so that they could be rich, yeah, by just triggering this kind of integer on the underflow variability. So I inserted this challenge to you guys to learn about like this kind of the integer underflow variability. So I will not trigger the flag output, but after making this kind of the score, and then if you quit the program, then like you will get the flag by making your score as bigger than like around 4 million. I'm not sure like you guys can even reach the maximum score more than that number, but my intended way to solve this challenge is like the triggering integer underflow. Any questions about this challenge? Yes. Yes, there's a since there's a one question. Yeah. Yes. Oh, that's also okay because like the 9 is an incorrect command. That's why you can get like the negative numbers like that. Yeah. Oh, so like you mean that like you try to like inject the weird input to the program, and then like the program interpreted that as a wrong command, and eventually like deduct your score and make your score like big enough. Yeah. So yeah, so you were lucky to resolve that. Yeah, so I believe like you could have like that kind of thing. Yeah, maybe like I can change the challenge to like having the intentional command to deduct the 0.1 from your score or something. Then like you would have like you are required to find the exact command to trigger the -1 value, right? Yeah, thank you for letting me know about that. And about the question from Stan, will AFL find this? Yeah, I believe so. Yeah, if the AFL like as like the what Chan Yu did, yeah. So like if the AFL just inject like a long data enough to make the score as a -1, yeah, then like uh, yeah, or like the more like lower values as such as -2, -3, yeah, any kind of negative value, then like it will like give out the flag. All right, let's move to the next 5 get flag without write or nor exec. So I will skip the where to jump for the number 4, and then I will get back to that challenge later. Yeah, and for this challenge, so you can read about the readme, and it says it uses seccomp and set the policy on certain system call. And in the binary program, you can only invoke these 5 system calls: open, read, lseek, exit group, exit. Then like it asks like, can you get the flag file by exploiting the buffer overflow program? Yeah. And then it says like a core file will never be generated because like there is some of the flag related issues. So it will not give away the flag from the core file, but you need to successfully leak the flag. Yeah. So let's check the code first. So this is the source code, and in the main function, yeah, it will open the etc cat issue as a file. Yeah. So it just open, does nothing. Yeah. And then it will print out some of the output, and it will say like that you can run some of the system calls. So if you select 1, it will run set regid, and then select 2, then it will run execve, and then select 3, then it will write ASDF to the send that out, and then 4, it does nothing, and then it's just to run target. And before running the thing, it will run setup rules. And what this setup rules is like applying the seccomp, which is some sort of the sandbox that limits the execution of the system call. And then what it does is like it says the default action of the secure computation is action kill. So if any of thing is detected, then it will, if any of system call is invoked, then the default action for the system is killing the process. But if the system call hits these kind of the allowed, so seccomp action allow the system calls. So if the system call is for open, read, lseek, exit group, exit, then they are okay. But otherwise, it will kill the program. So that means that we cannot call write nor execve, those kind of the system call at all. Yeah. So that's the big, huge restriction. So, and then that means so that by pressing the 1, 2, 3, we can invoke these kind of functions. So it will invoke a set regid, execve, and then write. And then let's try to invoke that. So if we type 1, then it will run set regid, but it says a bad system call because this system call is not allowed. It will only allow open, read, exit, lseek, exit group, those 5 system calls. Set regid is not allowed. Execve is also not allowed. No. Even the write is not allowed. Yeah, we are not seeing ASDF at all. So all the things are bad system calls, so we can only invoke open, read, and exit. Then can you steal the flag? So let's get back to the source code again. Yeah. So what it does is like after setting up the rule, then it will run the target function. So the target function is this one. And what you can do is you can launch the buffer overflow vulnerability here. So by overflowing the buffer, and you can check the pawn, check sec. So this program is non-PIE, no stack canary, so you can freely overflow the buffer, and you can gather the ROP gadgets from the binary, and without worrying about the ASRL, you can use those addresses because the program is not a PIE at all. Yeah. So at here, by exploiting the buffer overflow vulnerability, what you can think of is like if you can run some of the ROP chain as open flag 0, then read 3, because it will return the file descriptor, and then file descriptor value will be 3 because the 0, 1, 2 is resolved. And then we can read some of the address, maybe some of the global variable address, something like this, and then size as some bigger size, bigger than the flag. And then write 1. This was like the open read write basic sequence of our exploit previously in some of the challenges. But the problem is that it does not allow us to invoke a write system call. And what we can call is lseek, exit group, and exit. So can we leak the flag content in this situation? So let's get back to the readme again. So what we want to do is we can call some of the ROP chain for the calling open flag, and then the read from flag to the somewhere and the location. Yeah. And then what we can do is, so because we cannot invoke system calls such as write, what we can do is we can actually call the access system call, and then pass the argument of the access system call as the first byte of the flag. So for example, so actually we can check the return value of the program. For example, let's write t.c. And then what we will do is, So we will just get the, and A is A to I of ARGB. So we will just translate the first argument as an integer and then use that as an xcode. So what we will do is like a --t1, then this actually call exit1. And then if we do --t2, then it will call exit2. Something like that. Then suppose like how we can use about like this kind of the thing. And then, yeah. Right. Stan says that this is cool. So this is somewhat like a somewhat side channel attack that you can leak the flag content even if like you do not have the right system call, but with the xcode. And then how we can use the xcode is something like this. So if we can run t1, then we expect the xcode as a 1. No, maybe this one. Yeah. So if we do echo $question mark, then that's actually showing the return value of the program. So for example, if we run the T100, then it will show 100. And you can even get that information from Python. For example, you can, if you run the system, that's T100, maybe import OS and OS.system, then its return value is like the actually 100, but the returns at 256.00. Maybe. I don't know why. Yeah. So it actually, this will be the return value. Yeah. Divided by 256. So not really, maybe. Yeah. So something like that. Yeah. So it can only return a 1 byte. That's why like it does not work for the bigger value. But something like this, we can get the exact value. So we can get the return value from like the return value of the program. So what you can do is like you can run this program in the Pawn tools, and then after this program returns, then you can get the return value. Yeah, and then by examining the return value, the exit code. Yeah, by examining the exit code, you can leak the flag value byte by byte. And then after collecting all the bytes, then you can get the flag and then authenticate that in the CTF, that unexploitable.systems. Any questions to this challenge? So the important part is like even if we do not allow the system calls for dangerous system calls such as a write or execve, if there's any system call that we can deliver some of the value out of the program, so such as an access system call, then attackers will can steal the value byte by byte. So for the security, so it's the best security is to protect all the things. So if we leave any kind of the hole, then attackers might play with that and then steal the important data. That's the lesson. And the next challenge is about the 6 deprivileged. Then let's take a look at the deprivileged.c. Yeah. Then in the main function, it will open the file called the good luck, and it does nothing about the file. And then if there's a file, then, oh, you have a file named the good luck, wish you good luck. Yeah. Yeah. And then what it will do is like after running this, it will print out hint. And then what hint says is, so it will get the prop file system and with the current PID. So it will show like what kind of the file descriptors are opened for you. Yeah. So that could be a hint. Yeah. And then after printing the hint, it will deprivilege. So it will run set regid, but the problem is that it will run get gid, not get egid. So this actually means that the program itself has an effective gid as the gid of the flag file. But the problem is like if we run set regid with the get gid, then it will overwrite the effective gid as our gid. Then the my GID and then effective GID will be the same. That means like we cannot open and read the flag file after this point. Yeah. So in the target function, yeah. there is a buffer overflow vulnerability, so you can run whatever you want. So maybe you want to run open read write or like those kind of the system call or like the execve. But no matter what you do, like you will get the privilege of the GID, previous GID. But how you can approach about like this challenge is that, so the important thing is like the Linux is a capability system. That means it will check the privilege of your group ID or UID when we open the file, and then after opening the file is completed on accessing the file, for example, running read and write. Yeah, it does not check the privilege at all. So that means, so right now it says my GID is like the 1070, and then my EGID is 1070, which is like the same as my GID. So even if I exploit the buffer overflow vulnerability here, then the GID and then EGID is the same as my GID, then I cannot read the flag. But the interesting thing is that, so at the start of the program, it will open the file called good luck. And then what will happen if we create the symlink flag as a good luck? To do that, we need to wrap this as a quote to include the white space. Yeah. Then we have a file good luck as a flag. And then if we run deprivilege it, says like it has a file name called good luck. And then it says wish me good luck and then print out hint. And then to see the hints correctly, we need to run the deprivileged copy. And because like right now the process is running with the higher privilege, we cannot read that. So let's try to run the deprivileged copy. I don't know why it does not print out the hint. Yeah. Let's take a look at the deprivileged copy, and I believe it opens the file good luck. Yeah. I don't know why, but let's check it. So the deprivileged copy is running it here, and then what we will gonna do is proc PID FD. It didn't open the. Oh, the reason is like the flag file is not available for our privilege. So what I will do is remove good luck. Yeah, and then I will symlink readme as a good luck. Yeah, and then if I run deprivileged copy, then because it opened the readme file, the good luck, the file, then the number of the opened file for this one is like the 0, 1, 2, 3. So it already opened the file readme here. So right now, the reason why I changed the good luck to readme is like the flag file is not available for open for this file. But if we this file is the same file with this one, but just with not with the GID privilege. So if we run this program with the good luck linked to the flag, then your file descriptor 3 will be already opened for the flag file. Yeah. So let me describe about the reason. Yeah. So at the start of the program, it will start at the main function. At this time, we have an effective GID. So even if like our good luck file points to the flag file, we can open that. So at this time, it will check the GID, and then operating system will allow us this program to open the file. And then after opening the file, its file descriptor will be the 3, and then we deprivilege the program. And then even if we deprivilege the program at this time, because the file descriptor 3 is opened and then all the security check happened at here, so you can actually, so after you get to the target function, so if you can exploit the buffer overflow vulnerability here, and if you can play with the read and write system calls to read the data from the file descriptor 3, and then write the data to the console, yeah, that's actually possible. Because while you are making the read system call, there's no permission checking at all. The permission checking happens only at the open system call for the file system. So what you can do is like we can open the flag before deprivilege happens. And then even if the process is deprivileged, then you can still use that file descriptor at here. So that's the main thing about the challenge. So it's about the practicing that reusing some of the previously opened the file descriptor before like getting the deprivilege from the program. So the lesson is like if you want to deprivilege one of the process in the middle, then you need to be aware of like what kind of files are already opened, or yeah, and then you need to close some of the sensitive file descriptors, preventing the access of them from the attackers. Any question to this challenge? Right, let's move to the next. Next is about the TOC, TTOU, time of check, time of use, kind of the vulnerability. And let's check the source code first. And then source code is quite long. And then what it does is this is the main function. And it says it's a secure file reader. And then hint is to exploit the time of check, TOC, to the time of use, TOTTOU bug. And then you will see that what is the time of check to time of use bug in the code. Then I will exploit that. And then what it does is like it will get the file name that you would like to open. Maybe you want to type the flag here. Yeah. And then after getting the file name, yeah, there's no buffer overflow vulnerability at all because the buffer size is 512, and then what we can put is like just 100. And then after that, it will stat the file. So this is the time of the check. So it will check the file name, then get the information, and then check if the file's GID is the same as my GID. So that means the GID of the flag file is not our GID. Yeah. So that means we cannot read the flag file, but we can read our own generated file. Yeah. So that's the check. And then if we failed on the check, then there's a problem. Yeah, we cannot, it will just exit one. And then after 3 seconds of the super secure processing, yeah, it does nothing for the 3 seconds, then it will open the file and then read the file and then print out the value. Then what is the time of check to time of use bug? So time of check is like a checking of the privilege. So time of check is at this time. But after the time of check, and then before having the time of use it here, so between these two time of check and time of use, we will have the gap of 3 seconds. Then what if we can change the file between these two? So for example, we can type a symlink A, and then at the check time, we can make that check goes to our own file. So symlink the file name A to our own file. And then within the 3 seconds, if we change the time of, before the time of use, if we change the symlink to the flag file, then we can read the flag. So that's the time of check and time of use vulnerability. So when we check the security, then we can supply the legitimate value, so our own written file there. And then when the program uses the file, then we can change the file to the privileged one to steal the flag. And then let's practice about this. So what I will do is like I will create the, as we always do, I will create the fake flag. So here's the fake flag. So if you just get cat fake flag, and then it says fake, here's the fake flag. Fake flag is here. Then I will create the symbol link A as a fake flag. And then we can run talk to, and then type the name of the file as A. Then because that is our own generated file, fake flag. So same group ID, and then it will just print out the fake flag is here. Yeah. And then what we will gonna do is, so during this processing, we will change this A to the symlink to the flag. And what we can do that, how we can do that is like just open the tmux, and then what we will do is like we will write a command rm A, and then dash S flag A. Yeah. If we run this, then our A will be changed to the flag. But so I will make this ready, yeah. And then I will remove A. I will just set the A as a fake flag. And then what I will do is like I will run the tocto here, and then I will give the name as an A here. And then during the processing, I will run this. Then this will change our similarly linked A to the flag. Then at the time of the use, it will just use the flag file. So if we just having this A as a symbolically linked to the flag file, so it says the my GID is this one, then the file GID is this one, so it is rejected. But if we exploit the time of check to time of use, this 3 seconds of the secure processing, then having the race condition, yeah, we can win the race, and we can steal the chance that injecting the flag file for the opening. Any question to this challenge? So this is actually an easier version of the next challenge. So because it has this kind of the 3-second gap, so it's easy to exploit. So with some of the hand, yeah, by opening the tmux and then preparing some command, you can exploit that. And the more interesting version is like this one, caffeinated talk to. The reason why it is caffeinated is like it does not have a slip at all. That means this is actually the same code, yeah. And then there's a no slip, yeah. So there's a time of check and time of use, but there's a no slip. So because the time of check to time of use is quite fast, you cannot get the chance to win the race by hand. So what you need to do for solving this challenge is like you need to write a program to automatically generating the some link to the your own written file and then to the flag and then change it very fastly. Then like if you can get a window that like a time of check and time of use, then if you switch that as a fake flag to the flag, then eventually you can get the flag. So you need to try some of the attack multiple times to get this challenge. But the basic idea is like you need to flip the symbol link to the URL file to the flag, and again and again, switching between these two again and again, then to get the chance for the race condition. All right, that's how you can solve a caffeinated talk to. So this is actually the important class of the variability. So when the multiple thread working all together, and also like this kind of the some of the program waits for the other thread doing something, there could be the race condition. So you can apply this kind of technique to attack other programs. So in a single thread learning or running of the program, so there could be no variability at all. But if the environment is changed to like running with a multiple thread or something, so even if like you have no vulnerability in the single thread execution, there could be vulnerability introduced by like having the multiple thread or processes. That's the lesson that we can learn from this kind of the time of check to time of use vulnerability. Then next challenge is titled as a guess password. And what it does is like it has some of the predefined password. The password is definitely not 0000000. I just wiped out, yeah, from the source code. And then what it does is like it mimics some of the Ubuntu login page, and then it will get the character by character, and then if that character is equal to the cur is the password, yeah, and then the password cursor will be moving by one with this for loop. So by character, it will compare the password character with your input, and if it is correct, it will uslip this much, like it's around 0.2 seconds, yeah, and then get the next character. If it is correct, wait for 0.2 seconds, and again. But the problem is like if we mismatch the character, then it will just break and exit. And then if the current is end, that means like if we correct all the, like if we get all the password correctly, then it will open the flag file and then print out the result. So it's about like guessing the password, but the hint says like that this timing delay makes the challenge easy. So the thing is basically that if we made a correct guess, then there will be like a 0.2 second of the delay. But if we make it's not a 0.2 second, like a 0.02 second, I think. It's a 20 millisecond. So it's quite fast. But if you can observe that delay with some of the programmatic timer or something, then you can actually distinguish if your guess is correct or not. So let's try to do that. So you can actually write a Python program to measure the time, but I will demonstrate how you can check if your current guess is correct or not by hand. So there's a program called time, yeah, and then like by having a echo a, so we can make a as a guess for the program for the first character, and then we can test that like this. And then if you apply the time program, it will measure the elapsed time for like the execution of the entire of this program. And then output is somewhat like the weird, but how you can see the entire running time is like from this timer. So if I type A, entire running time is around 0 second. It's quite fast. So maybe I can change it to B, 0 second, like this. C, 0 second. And then I can do that again and again. Maybe P, 0 second. Q, 0 second. R, 0 second. But if I type S, then 0.02 seconds. So the sleep happens only if we make a correct guess for the character of the password. So we can assume that the S is the correct first character. Maybe we can try another character, OPQRST. Maybe T? Yeah, it's 0. So only the character S can get the correct character. And then we can make another guess as a SA, SB, SC, something like that. But I did it previously, so the character W will have a different timing. So it's something like you can loop over each possible character of the password, and then if you can observe like this kind of the execution time difference, this kind of delay, then you can assume that that's the correct guess. And it's about like you need to make a correct guess for like the password byte by byte to get out of the entire password. So some of the secure like authentication algorithms in like the several years ago, some of the bad design was like the applying the complex encryption algorithm. So if you make some of the wrong guess, the algorithm kick out you fastly. But for the making a correct guess, because the cryptographic algorithm need to be executed at the end. So if on the slow processors, it's enough that the attackers can detect this kind of the delay between the correct guess and then incorrect guess, so that could lead as a leaking of the correct password like this. And I inserted like the sleep 0.02 seconds, so 20 milliseconds per each character, as like the mimic that kind of the slow behavior of the encryption algorithm here. So it's the simulated challenge, but that you guys can learn about like that kind of the slight delay. So even if it is like the 20 milliseconds, if you can detect that as a program, then like you can use that for like a side channel attack, and you can leak the password. And the next challenge is a more straight challenge. So like a challenge says like Rob static, and one of the special thing about this is like if you check the size of the program size is quite small. So it's just a 1.6 kilobyte. And then the reason is like that this program is not a dynamic binary array at all. So that means that it will not load any kind of library. So the program itself is like an entire thing about the program. So that means if we run the program with GDB and then break and main and run it, and then if I run vmmap, then like there's no library at all. So it just has a stack. and the code and data area. That's it. So we cannot use printf, execve, those kind of functions because there's no functions at all. So, but what we can reuse is like some of the code that is existing in the code. Yeah, so that we can reuse these kind of codes. So it has a string length function, so we can reuse that. And then there's a write, read, and exit, puts, those kind of functions. And then it has a main function, an exit. So we can reuse these kind of functions, but then nothing else because there's no libc. So this is a challenge that there's a buffer overflow vulnerability in the main function. So it has a read function to the buffer. While the buffer size is a decimal 200, it gets a hexadecimal 200, which is a 512. So you can have a chance to overflow like 312 more bytes. Yeah, and then at here, you can develop your own ROP chain to run something meaningful at here. Yeah, but the problem is like you do not have open system call here. You have a write and read, but no open or nor execve. In this case, can you run your shell and read the flag? That's the challenge. Yeah. And then from the README, you can find some of the hint. Yeah. And then this is how this program is built. So to build this program, I set it as a 32-bit binary, and then like it is a static binary. It does not include any kind of library, and also it does not include the standard library at all. So that's why this program is very small without library at all. Yeah, and then yeah, and then like to exploit the vulnerability, what we want to do is like either run execve or open read write. But the problem is that like, we can do read and write, but we cannot call open because there is no link to the open system call at all. Then there is no execve system call at all. Yeah. But you can invoke system call by using the gadgets. The thing is, so from the code, you can identify there's a int 0x80. What that means is that, so in 32-bit the x86 program, so I will just disassemble write function. And then what it does is like before invoking the write system call, what it does is like it will set the EAX as a number 4 write system call. And then it will set EBX, ECX, EDX as like the corresponding system call arguments, right? So basically what we need to do is like we need to set EAX, EBX, ECX, EDX, and then jump to int 0x80. Then, so I just told that like there's no execve, but that the system call number for the execve is 0xp. Then what if we can make the EAX value as a 0xp, which is 11, and then return to this instruction into 0x80. And by just setting the EAX value to this one and then into 0x80, that actually means like invoking system call for execve. So even if there's no execve open those kind of the functions, what we can do is like if there's any way that we can set the EAX value as like the arbitrary value like this, then yeah, we can invoke the system call. One question is that where did the 0xp comes from? Yeah, I will show you. So so let me share my web browser. Yeah, Linux system call number 32-bit. So this is a 32-bit Linux system call table. Yeah, and then number 11 is execve. So the 11 is 0xp in hexadecimal. That's why. Yeah. So what we can do for like an invoking system call in 32-bit is like just setting the EAX, BX, CX, DX, those values. So if we can set the EAX values as 11, then if we return to int 0x80, then that's the running execve. Yeah. That's the point. And then the next thing is like then how can you set the EAX value as an 11? Yeah. Then you might want to refer to the ROP gadgets binary and then ROP static. Maybe we can get the ROP gadgets at here. And then you may search about like some of the gadgets that manipulate the EAX register values. Then it has some of the EAX, something like the move the ECX value to EAX. Then if we can set ECX as an 11, then we can invoke this point. Then the ECX will be moved into EAX, and then do this pop return. Yeah. So you can regard the add ESP 0x28 is like is doing like a lots of pop up to size 0x28, and then pop ABP and return. So you can regard when you write the ROP chain after calling that gadget, and then you need to have some of the gap to handle this kind of the add ESP. So you can use this gadget to set the EAX to value of the ECX, or you can use some other values like this, but these are related with the memory dereferencing, so it's quite difficult. And then other things are with the fixed values. 4 is a write, 3 is a read, and 1 is exit. So these are for just in invoking the system calls that the function that the program is using. Then the next is about how we can control ECX. Then let's search for the ECX. And is there anything that we can control the value of the ECX? No. So it's quite interesting. We cannot control the value of the ECX. That's the problematic. Yeah. Then how can we control the value of the EAX? So the important thing is we need to make the EAX is not 1. It should be 11. Then we need to return to int 0x80. And the hint for that is also included in the readme file. So the first hint is about the invoking system calls, but I just described it. So to invoke arbitrary system calls, if you can set the EAX value to arbitrary 1, and then other arguments as an arbitrary 1, then you can call any kind of system call. And the next is about how can you set the EAX register value. Yeah. So we could not find the gadget to control EAX to be 11. But the interesting thing is that the EAX register is used for putting the return value of the function. Yeah, this is a typo. Yeah. So what that means is that if you can control a function to return 11, then if you make a function call, and then if you get the some of the return value as an 11, then your EAX register will have the 11 as the value. Then right after that, if you return that to the int 0x80, then that will call execve. Yeah, that's the one of the things that you can use. Yeah. And then another thing is based on this kind of the memory dereferencing work. So it actually dereference load the EBP -8 to EAX, and then pop return. Yeah. And if you can control the value of the EBP to where the value stores 11, then you can use the gadget and then setting the EBP correctly to set the EAX value as an 11. But you can use either one of the method, and then try to think about using the return value thing. Then you can go back to what are the programs that what are the functions that you can call. Yeah. So you can call write and read or something like this. But think about the return value of the write system call, yeah, or read system call. So suppose so right now we can call the write system call, yeah. And then what if we make a write system call for something like this? So maybe we can write a function like this, and then we will call write system call, then to the standard out, and then we will type some of the output, but just for 11 characters. Then we will store return value like this. Then we will just print out the return value. Yeah. Make the T and then run it. Then the return value is 11. The reason is, let's take a look at, and then we will just break at the main plus 28 right before calling the write function. So in the write function, we set the argument as a standard out, sum of the buffer, and then size as a 0xb. Then after running this function, because the write function is supposed to return the number of bytes written as a return value, So our RAX value is 0xb. Yeah. So what we can do is, so to control the EAX value for the arbitrary one, what you can do is when you are exploiting some of the vulnerability at the here, buffer overflow vulnerability here, if you can develop the ROP chain after setting all the arguments for execve, for EBX, CX, and DX, and if you can run this, is that read or write with the length 0xb, then return value of this one will be the 0xb, then that will set the EAX register value as a 0xb, and then after that, if you return to either one of these int 0x80, then it will run execve. That's how you can get the execution on this static binary. Any question to this challenge? So the important thing here is that how you can control the value of the EAX. And the lesson here is that even if there's no gadget to directly control EAX, don't worry about that, because the EAX or RAX, that's used for storing the return value. So if you can control the return value in like in other manner, yeah, such as like the printf or write, read, those kind of functions. If you can make it return 11 or like the 5 for the open, yeah, then you can run that system call. And then the last one is where to jump. Yeah. So let's check the check stack of the where to jump, and then it has a stack canary, and then it has NX enabled. So it has no PIA. So we can reuse some of the code region of this program, and then let's check what this program is doing. This program is very short, and then in the main function it directly calls a target, and then in the target, so it says jump game, and it says give me an address to jump, then I will jump for you, and then it will get an address as an hexadecimal integer, and then it will print out as an hexadecimal integer, and then it will just jump it. So for this program, we do not have like a capability of the arbitrary read nor arbitrary write, but it directly gives us like the arbitrary code execution, but in a limited fashion. We cannot inject the code, but what we can do is like we can specify EIP. So what will be the instruction pointer that it should go to? Yeah. And then so maybe like this would feel like a little difficult to you guys, because like it just says like where to jump, but not about like so not about the details of the attack. So if you have like the arbitrary read or arbitrary write or like the kind of the functionality, then what we can do is like we can overwrite the return address of the target to call the target again. Then we can make this kind of the vulnerability exploitation as multiple times. Then like we can do more interesting thing. But the problem is like if we set the call target as a target function, then it will call target and ask, target and ask. That's it. Yeah, there's nothing that we can do. Yeah, that's one of the problem. And then another problem is that when we overwrite the return address for buffer overflow variability. Yeah, so we try to run multiple ROP gadgets as a chain. But here, what we can specify is just one address, not the chain of the address. So that's the problem. Without the chain, even if like the ROP is powerful, we know how to do that. If we cannot construct a chain, then we can just run one ROP gadget and that's it. So that does not constitute a successful attack. And how can we develop the attack for this? So this is actually a trick challenge. So you actually need to run the ROP chain for the entire challenge, and there's no README at all. But the thing is, like what you can do is like you can build a ROP chain and place that somewhere on the stack. Yeah. So the interesting thing about the ROP chain is like that we are not actually executing the ROP chain itself. ROP chain stores the address of the code, and then we are actually run the code pointed by the ROP chain. Yeah. So the ROP chain is okay to be read only. Yeah. So what we will do is, so we know how to place some of the additional data on the stack by exploiting the environmental variable or like the as a argument. So it's something like our stack will be here. And then if we place something at the environmental variable, then those data are like somewhere here. So we can actually place our wrap chain here. And then if you jump to the special instruction, for example, add ESP big number and return. So think about it. So I will just wrap gadget binary where to jump, and then store that as a wrap.txt. And then I will search for the add ESP. Yeah. No, actually maybe this one. Yeah. So this instruction, return EAC1. So this return instruction actually, so this is a regular return. It's just a return. But this return instruction, return 0xEAC1, what it does is like it will skip the EAC1 bytes on the stack and then return to some address after that. So it's something like a big pop and then return. Yeah. And then how we can use this gadget is that, so suppose that we have a program stack here, and then we put some wrap gadget chain at the environmental variable. And then if we do the read EAC1, then it will return, skipping lots of bytes, and then return to here. Then it will eventually meet the wrap gadgets and then run the gadgets. So it's something like the challenge is about like asking if you know about like this kind of trick. So that I will just let you know about the trick itself. So what you need to do is like you can put your shell, the wrap chain in the argument or environmental variable or anywhere in the stack. And then if you can control like that will be placed exactly at the position of the when you use the return EAC1, this kind of the instruction, then it will skip the whole bunch of the data and then jump to the return from the some of the data up here. And then if you can control your wrap gadget chains are exactly at here, then you can get the shell. Any question to this challenge? I believe like among the other challenges, this challenge is quite tricky to get an exploit because you need to align your wrap gadget chains correctly when you use this return gadget. So the some other gadgets would be, so if we have some of the gadgets, for example, at here, we only have something like add ESP 0x28 pop EBP return. But if we have gadgets, right, like something like this, so add ESP to big number, then it will skip the big number of the data. Yeah, then it will eventually hit the our wrap gadget that we placed on the environmental variable area. Yeah, so we can either use like this kind of gadget if it is available, but otherwise we can use this kind of the return with the skipping some part. And also, if we can directly modify ESP, then that's another thing that we can use. But there's no move ESP instruction, so it's putting the ESP to EBP. It's not changing ESP. So if there's a instruction that you can change ESP directly, then you can also use that instruction for the attack primitives. Yeah. So the one question from Philip, I loaded shellcode in the environment and tried to call it, but data stored in the stack randomized address. So one of the problem is that you cannot use the shellcode. So because the binary itself is with the non-executable, right? Yeah. So non-executable is enabled. So yeah, you cannot use a shellcode. So what you need to do is like you need to develop all the wrap chain and then put that into the either environmental variable area or in the like the argument, and then like the when you return from the program, yeah, the function, then the size is like the EA01 or something, then your stack address plus that address. At there, you need to put your wrap chain. But the important thing is like the even if the ASRL is in place, the relative offset from like the current function return to the environmental variable area or like the argument area, these are for somewhat fixed. So like you need to exploit that kind of the fact to control the location of the your wrap chain. So the interesting thing is like at this challenge, you need to upload your wrap chain in the stack, not the shellcode. So any other questions?
Yeah, Professor, I have a question.
Yes.
Because actually I spent the night. I solved the TOC TTOU and caffeinated TOC TTOU. But in my case, I just used the LNS the flag, and then also I make some file LNSF. Yeah, because I set up the both symlink to the multiple the files, and that the split the many windows and that with for loop for close in the Linux, I run multiple times, even if 100. It's the same things.
Yeah, I think basically the method is similar. So what you can do is something like, for example, like what you want to do is like writing a Python script, something like this. And then in the script. Yeah, and then what we will do is like the import OS, and then os.unlink A, and then os.symlink flag A, and then os.unlink A, and then os.symlink fake flag A, something like this. And then we will do something like this, right? So it will in the loop and then keep changing it. Yeah. And then what we will do is like the touch A, and then vim fake. So we have a fake flag and the flag here, and then open the tmux. Then I will just run the eda_py on the right side. Yeah, and then we will see that no, A is not available. Why? Maybe my program is wrong. Let's check it. I think it's correct. Maybe let's check with this port OS. Then here you're not seeing A at all. Then what we will do is os.symlink flag to A. And so we have a flag. Then A. We have no A. Then link the fake flag. Then we have a fake flag A. Yeah. Then so in the eda_py, what we'll do is link and link and link and link. Yeah. Run it. So basically the important thing is like it will create the symlink repeatedly, and then if you run the caffeinated talk to of the multiple times. And then if you hit the correct window. So right now I hit the wrong window. My GID is this one, and then the target file was a flag, so I failed it. Yeah. So easy way to run it might be the maybe you can do something like this, and it will automatically type the file name A. Yeah, and then you can run it again and again. Then like so right now it just read the fake flag, but you could have a chance that like the program runs make use of the flag file by using this. So it could be rare, but you can get the chance. But the interesting thing is like you can run it again and again, but you can examine if the output contains the canned with the braces to check like the flag is there automatically.
Yeah, actually, many for loop I got
right.
it. So
you can write
I
a
need
program
to,
for it.
Yeah, I need to
That's
understand
the right way.
how do I did it. So
yes.
Yeah, by the way, one more question, because actually I love the 9 challenges. I really enjoyed that, the guess password. Yeah, but I'm actually at the first time I didn't see the code. So kindly, Professor, you put the sleep to 20,000 in the code, right?
Yes.
It's a 0 point
it's 20 milliseconds.
0.02, yeah, right.
Yeah.
So yeah, but normally we don't have that kind of the code.
Yes.
So actually, in my case, I run 100 times and then get the average on every letters. So because I spent the night to get that value, but I realized that in some cases, even if some letter is not the password that I think, it was spiked.
Yes.
What's the reason?
It could be because some of the pipe could be delayed, and then it could be affected by the other people's execution. So sometimes the machine could be slowed down if there's a lot of processor going on, because the machine is just a 4-core, and then we have around the 30 students, so that it could happen. So your system could be slowed down. So the correct way to do that is like the interesting thing is like no matter how many times you check for the correct password, you will have delay for all time. So what you can do is like if you observe like some of the delay, then try that character for 100 times. And then if you observe like any kind of the fast return, then like the 0.02 seconds, then that means that's not the correct guess. Yeah, for the correct guess, you will always observe like that kind of delay. So you can prune out some of the false positive data, right, like that.
Okay, got it. Thank you.
Yeah. All right, is there any other question?
Just real fast, is there anything for this side channel challenge that prevents reversing for the password? I haven't looked at it yet, but it seems like this might be possible.
So what I did is like I did not give the read permission to the binary program.
Ah, okay, that makes sense.
That's why.
Yeah, thank you.
Yes. But there's a way that you can leak the binary program even if you do not have the read permission. So you can actually solve this challenge with that method.
I've done one blind. That was enough for me.
No, it's not the blind challenge. So the interesting thing is that like in Linux systems, and then in all of the x86 systems, the execution privilege solely having the execution privilege in the memory implies the read privilege. So at the CPU level, there's no restriction that prevents reading the data from the executable only process. So it's something like you can actually leak the binary content, yeah, by exploiting some of the system weaknesses. So try that, yeah.
Okay, I have to read about that. I don't know enough, but that's
And
interesting.
then one hint is about like using ptrace.
Oh.
Yeah, you can use ptrace to debug the program.
Yeah.
And then you can leak the binary from there.
Oh yeah, so if I run it with GGB, would it work fine, or do I have to?
So GDB will fail to attach because it has a no read permission at the start. Yeah, but there are some ways to do. Search about that. Yeah.
Okay, I will. Thank you.
Right. All right, if there's no more questions, let's finish our tutorial here. And then thank you so much for playing the challenges so hard. Yeah, I'm also enjoying that whenever you guys submit the flag during the night. Yeah, I feel like that is a good sign that you guys study hard even for the nighttime. So yeah, I'm sorry for making you guys working hard at night, but hope you guys enjoy all the challenges and have fun, and also learn lots of things about the how the binary pawnable attacks are working, and then how the what is that, the defense mechanisms are working, and also how to break them. Yeah, thank you so much. Yeah, thank you so much for the compliment. And then I'm so glad to hear about you have a lots of fun with those hands-on exercises. So I will upload this tutorial tonight. There will be some of the delay that the Canvas cloud service processing the video. So and then you can watch this video again to tackle with the Week7 challenges. And the important thing is that there will be no late submission for the Week7 challenges, but the deadline for the Week7 is next Friday. So please take enough time, and there will be no final exam. So please have fun with those challenges. All right. Thank you so much.